Hi. In the book, there's this section on the problem of alternative constraints. It's in Chapter 6, Section 2, and I wanted to give a little talk or review of that and try to bring out some of the high points. So this is really a very general application because any non-convex optimization can be divided up into a problem with alternative constraints. So this star-shaped region, you can see that it consists of two triangles, and everything in the star is in one triangle or the other, or in both. And so we get this non-convex region as a union of convex regions. And you can think you can have some very complicated non-convex region, and if you can divide it up into triangles, that means we can formulate it as a problem with alternative constraints. And the triangles don't even have to be connected. I could have one triangle over here, one triangle over here. Right? So the point is, how do you formulate this problem with alternative constraints? All right, so here's the basic idea. So here I'm just doing a case where you have two regions, a union of two regions, but you could use the same idea for a union of arbitrary number of regions. So the basic idea is to create two versions of each constraint, one which bounds one of the regions and one which is satisfied by all the points in all regions. And then the second idea is to use 0, 1 variables as switches to switch between the two versions of each constraint. So we have to have variables that take the value either 0 or 1. So this is an integer programming problem. It's an integer programming problem with limits, right? You can't have any integer, but only the integers 0 and 1. Okay, so let me analyze this particular example here where my actual region is the union of region 1 and region 2. So it kind of looks sort of like a bow tie. And we're also supposing that x1 and x2 are positive. Right, so let me implement these two ideas that I talked about here. So you can see region 1 is bounded by the two axes and this slant constraint here. So what I'm going to do is create another version of this slant constraint that includes all of the points in both regions. All right. Now here I chose it with a lot of leeway. I could have chosen it smaller, but it really doesn't matter. As long as this second constraint includes all of the points, that's all that's needed. Okay. And then for 2, I also have versions of these constraints. You see this constraint, if I push it out, it goes here. If I push this constraint out, it's going to go there. So we'll see that in a minute. So here are the original constraints, the bounds of the region, and here are the what I call lenient constraints, and all points in the region satisfy these lenient constraints. Okay, now the 0, 1 variables, I'm going to let y1 equal 1 correspond to being in region 1, and y2 and 1 correspond to region 2, and I need to have at least one of these be 1. Okay, all right, now, so as I mentioned, this red constraint here, it's x1 plus 2x2 less than or equal to 2. And then when I push it out, I have a larger constant here as the bound. Now I can combine these two constraints in the following way. x1 plus 2x2 is less than or equal to 2 plus 8 times 1 minus y1. So what does that mean? When y1 is equal to 1, and in other words, when I'm in region 1, then I have x1 plus 2x2 less than or equal to 2. So it has to be inside this region. Okay. Now, when y1 is 0, then it has to be inside here. So if I turn on the constraint, then I have to be in this region 1. If I turn off the constraint, I can be anywhere. Okay. Now, if I turn off the constraint, I want to turn on the other constraint, right? The other constraint would be would correspond to y2 equals 1. All right. Now, the two original constraints for region 2 are here, x2 minus x1 less than or equal to minus 1, and x2 minus, x2 minus x1 less than or equal to minus 1, and x1 plus x2 is less than or equal to 4. Those are these two original constraints. Okay. So let me create lenient versions of those two constraints. This x2 minus x1 less than or equal to 1, that's this lenient constraint here. And x1 plus x2 less than or equal to 5, that's this lenient constraint. So all points in both regions satisfy these. Okay. So when I turn on the constraint, that's y2 equals 0. Okay. If y2 equals 0, I want to have the minus 1. and the 4. So you can see that here. When I turn on y2 equals 1, then the -1 and the 4 constraints are operative. If I turn off the y2 constraint, then I get the lenient constraints, and everything satisfies. Okay, so the last step is just to make sure that either y1 or y2 is switched on. So you have to have y1 plus y2 equals 1 or greater than or equal to 1. At least one of the constraints must be turned on. If you turn off both constraints, then you will allow too many points. Okay, here you can see that I did 2 regions, but in fact, you can use the same strategy to do more than 2 regions. You'll have several y's, one for each subregion, and then you'll have to make sure that at least one of the constraints is turned on in order to include all the regions and not to include any extra points. All right, so that's pretty much how it works. All right, thanks, bye.